Hello, my friends. We are live. God, it's been a while with the holidays and all. We are live on the broadcast. Call it what you will, with Doug Arion, who's an astronomer and a friend of mine. Uh, he has been a guest on my show a number of times. I've gone up to his cool place in the White Mountains where he has an observatory filled with telescopes he's built himself. And what we're going to talk about today is the amazing James Webb telescope. And we need to find out why it's amazing and why the things that it can do are important, and also some of the things that can go wrong, what we expect the telescope to do. People may not understand that there are 300 plus functions that have to go correctly for the thing to even work, which blows my mind. I don't see how that's possible. With the Hubble telescope, which preceded it, they didn't even get the mirror right on that one, right? That was a basic thing they got wrong. I don't see how it's possible at all. The things that are supposed to go right with the Webb telescope but we'll see. So thank you so much for being with us, Astronomer Doug Arion from the wilds of the White Mountains in New Hampshire. You're actually at Bretton Woods now.
That's right. Oh, thanks, Bradley. It's great to be on again. I've enjoyed every one of our visits over the last couple of years, and to be able to talk about Webb is really, really cool.
I must say that I really appreciate the interest you've taken in my interest in science, and you've really brought me along and answered all my questions and encouraged questions, and even recommended the most difficult book that I've ever read. And I plowed my way through it over a couple of months with your encouragement, and I want to thank you for all that. Now, the James Webb telescope, why is it such a big deal? And what will it do? And why are the things that it will do so important?
So there's a lot of astronomy we can do from the ground, right? You're used to telescopes and observatories on the ground. But there are many things we can't do from the ground because the air is in the way. The air is shaky, and the air only lets certain kinds of light come through. So going into space lets us reach things and do things that you can't do from observatories on the ground, which is why Hubble was so great, right? We launched a telescope, not even all that big. I mean, very big compared to a backyard telescope, but professionally it wasn't that big. But being outside of the air, it could see lots of things that we can't see from the ground. So James Webb is a very big telescope. The size of Hubble was 94 inches, 8 feet across. This thing is 22 feet across, so much, much bigger. Number one. And number two, it's being designed to look at both light that we can see and the light that's longer than what we can see, what we call infrared, the stuff that glows. Like if you're using night vision goggles, the fact that you can see things that are warm but are otherwise invisible, just like your night vision goggles, it's able to do that. So Hubble couldn't do that. Hubble was designed to look at other things. So seeing this is really, really cool because we're going to be able to look at things that no telescope can see right now. And here are those couple of things. The first is that stars, which are very bright when you look at them, actually aren't that bright in the infrared, but planets are. So we might be able to actually see planets going around other stars directly, not just infer their existence or get a little hint of it, but actually look at a planet going around another star.
Why would that be important?
Well, we still want to know a lot about, we're a solar system. We've got planets. We have life on this planet. Presumably, you and I think, are living. And we'd like to know about that elsewhere in the universe. But the only way to do that is to actually observe what's happening on the planets around other stars. And right now, we don't have a capability that can do that directly. And this will let us do that. So that's one very important job for this telescope, is to actually look directly at planets going around other stars. The second thing, and this goes back to some discussions we've had in the past, and you can tell people about some of those interviews we did, because the universe is expanding, everything gets what we call redshifted, right? So if you look far away, the light that came out that was what we call normal light, right? The light that you can see has been stretched and is now infrared light. So if you want to look out really, really far and what happened near the beginning of the universe, you need to be able to look at stuff that's beyond red in the infrared. So for example, we know there are stars, right? You look up in the sky, you see stars. But where did the first stars come from? How did stars first form? We don't know because you can't see them. We haven't been able to see them yet because we have to look very far back in time. And that means they're really, really faint and they're in the infrared. So this telescope is going to fill in a big gap, right? We can see nearby stuff with any telescope, farther stuff with something like Hubble, but the really far stuff, this gap of how did we get from radiation and gas to the first stars, is something that Webb is going to be able to do that no other instrument can do. And that's important if we're going to try to put the whole history of the universe together. It'd be like knowing your whole story. We know something about when you were born and where you grew up, but we don't know anything about you in elementary school. We pick you up in middle school. It'd be kind of nice to know what happened there, that led to everything that followed. And it's the elementary school part of stars that we haven't observed yet.
So usually the way they figure out what stuff in space is made out of by examining the light.
Mm-hmm.
And you're saying you can't really do that because the light's out of whack because it's all been redshifted, but the Webb telescope will circumvent that problem.
That's right. Right. It's designed to look at that light that has now been so shifted that we can't see it with the existing telescopes. Right?
And look at it optically?
Look at it. Well, it's in the infrared, so it will
okay.
then be collected and made into pictures. And as you said, spectrum of, break down the light and understand what's in it to tell us what those things looked like back then.
All right. Super complicated piece of equipment.
Yes, it is.
There are many functions that have to take place even before it starts to operate fully. Mm-hmm. What are some of the things that have to happen?
Sure. So the Hubble telescope with its mirror, which I said is about 8 feet across, one reason it was that size, it was the biggest optic that would fit in a satellite that would fit in the bay of the space shuttle. So we could launch it, right? It's as big as you could fit. So if you want to go bigger, either you need to build a much wider rocket, not a taller one, but wider to hold this thing. But that only would get you so far. I mean, how wide could it be? 10 feet, 12 feet, 15 feet?
Right.
This thing's 22 feet wide. You can't put something 22 feet wide, right? So you have to do it in pieces. It's the same way if you get a house, a modular house, they have to bring it in pieces. They can't bring the whole house. It wouldn't fit on a truck, wouldn't fit on a road. Same problem here. We can't fit it on one rocket. So there are two ways you can do it. You could launch up pieces and then in space put them together. Or in this case, you build it and have it fold up. And when it gets into space, it unfolds. So that's what this is. It's made out of individual pieces, which are all linked together with all these complicated parts. And then each of these pieces unfolds to build this telescope. And as you mentioned at the beginning, every one of those steps, it's where the mirrors go, where the optics go, where the sunshade goes, all of these pieces have to happen exactly on sequence to make it work. And we've gotten, luckily, very good at doing those things. When you think of the Pluto mission, it was completely robotic. Once it got to Pluto, the time to send a signal was so long. It had to do everything all on its own. And it did it perfectly.
Some of the functions in the Webb are done on their own because they're so important, as I understood. The optics of this thing have to be so precise. Like the Hubble was off just a little bit and it screwed everything up.
Right.
How do they have the joints in the pieces not cause distortion?
So the technology for doing that. So the good news is, over time, we've gotten better at doing things, right? And sometimes you get better by making mistakes. I have a good friend who says, you know what experience is? You get experience when you get what you didn't want, right? It didn't work, but now I know what to do.
Right.
And so, for example, the very big telescopes in Hawaii, the Keck telescopes, are made with mirrors like this, individual mirror pieces that fit together. And the SALT telescope in South Africa, and Ever Hobby. So over time, we've learned how to make the sensors to get these things to line up. So now that's well known. We've been doing that for decades. And of course, we have even better sensors now. So not a showstopper to say, oh, we're just going to do this and they'll line up. We have the technology to do it. The difference is, of course, you don't have a technician who can go up there and look at it and go, oh, let me make sure that's right. We have to automate it all. But the basic mechanics of doing those things have now been well proven beforehand. And of course, you test it on the ground, you hang it, and you say, go through the sequence. It's hard to do because we have gravity, but you do every possible test you can do, and then send the thing up.
What do you suppose the confidence level is that it'll all work? Do they think, 80% chance, 90%, 95?
I mean, I think it's a 95 or plus chance that it will all work, but I'm sure everybody who's working on it is sitting there chewing their fingernails to their elbows every time one of the steps goes, because you've done everything you can, but you just don't know, right? Until you actually go do it. But so far, the solar array has deployed correctly. They did a mid-course burn. The next thing is starting to deploy the sun shield. That gets started, I think, tomorrow, which is late today, our time. But tomorrow, the next flight day, they start deploying that.
You mentioned solar array. Does that mean it's a solar powered? It would have to be, I guess, because you just couldn't have enough power to have it keep on doing things on its own.
Right.
And it has to be shielded from the sun. Is that because it is super sensitive, or because it gets close to the sun?
No, because it's super sensitive. It's actually very far from the sun. It's farther away than we are, by about 1 million miles. I mean, not hugely. It's 1% farther, but it's out where we are. But because it's looking at infrared light, it has to be away from and shielded from anything that's producing heat, right? Because remember, your night vision goggles look for heat. You can find a warm body.
Right.
This thing is looking for things that are, relatively speaking, warm, and therefore you have to keep everything around it very cold, because otherwise you have something low. So that's one reason that it's not being orbited near Earth, because the Earth glows. If you were near the Earth, there'd be too much glow. So like Hubble, which wasn't looking at that kind of light, could be relatively near the Earth. It's only 250 miles, 300 miles away. It's not that far, right? It's actually closer than I am to New York. It just happens to be in space. But this had to be much farther away so that the glow of the Earth wouldn't be a problem, and it has to have a shield so that none of the heat from the sun and everything else reaches the telescope.
So that kind of answers my next question, I think. Why 1 million miles away? That's how far you have to get away from Earth so that the glow doesn't affect things?
Well, two reasons. One is you need to be farther away from the Earth, and then you need to go to a place where it will sit and stay. So remember, everything's moving. The Earth is moving around the sun, and this thing would be going around the Earth. So Hubble goes around the Earth every 90 minutes. The space station goes around the Earth every 90 minutes. But if you go out farther away, it would keep, some distance away, it would keep going around the Earth, and eventually the Earth would be in the way, right? I mean, this is why we have these shields up. So you need to be someplace where you can keep the thing shielded, point it where you want to point it, and have it stable. So it turns out, if you do the math, that when you have the orbits of multiple bodies, so you have the sun, you have the Earth going around the sun, there is a place where something can orbit along with the Earth, right? Go around, stay in the same place, and be stable. So if it moves over a little bit, it comes back. And there was a mathematician by the name of Lagrange who worked out this stuff. It's called Lagrangian mechanics. There's a place that's like that. It's 1 million miles from the Earth. So we're sending it out there because it will just sit there and do its thing.
Will it be in a geosync? Will it stay in one spot and go around fast, or will it stay in one spot and not rotate around with the Earth? Is it a geosynchronous orbit?
Right. It is far enough away. The Earth will be spinning below it, and the whole system will go around the sun.
So it'll find one spot in space and stay there.
Exactly.
The Lagrange point.
Right.
Who is James Webb? Why does he get the honor?
He was one of the very early directors of NASA and basically built what NASA became. So in the late 50s, early 60s, coming out of World War II, we built our rocket program, and the Navy had a program, and the Army had a program. That we had a civilian agency, which was NACA, the National Aeronautics, something I forget exactly what it stood for. And they were doing a lot of the test flights and the supersonic things and so on. And then as space flight became important. That all got melded together into a new agency called NASA, which of course is running Webb and did the moon landings and everything else that we've done, all these things we've done in space. And so he was the director who basically got the agency going. So a very, very important person in the beginning and the structure and the longevity of the American space program. So it was chosen to name it after him.
Wow. So we talk about it seeing back in time, correct?
Right.
Okay. So can you explain how that is? Because, and I hope that I'm not exposing myself as a terrible fool, but we can only see the light that comes to us. This takes 8 minutes for the light to come from our sun.
Right.
A lot longer, years, millions of years from further away. And so I don't understand how this is seeing any further. The light that comes to it is still traveling that same amount of time. It's only, maybe 1 million miles closer, which is nothing to whatever the light source is. How is it seeing back further in time? Because the light still has to get to it, but you don't see outwards. It seems like you're seeing outwards, but you're not. You're seeing the light come to you. There you go.
Right. So think about this. Just as you described, everything you look at, you see in the past. Like right now, I don't see you right now. I see you in the past because it's taken time for the signal to reach me from you. Right.
That's right.
So everything I see in space. Now, remember, the farther out you look, you're looking farther back in time because it's just taken longer for that light to reach you, right?
But you can't. Here's my beat. All right, you can't look further back. Okay, go ahead.
Right. But the farther away it is, there are two other things that happen. One, it gets fainter just because it's farther away. And the second is the light gets redder because the redshift is bigger, right? It's traveled longer, so the universe has expanded more. So optically, what you can see with your eyes, you can only see out so far because if you try to look farther, everything has been redshifted to the point that you can't see it anymore.
Oh, all right.
This telescope sees in the infrared, and so things that are farther away and therefore more redshifted are still visible to this telescope that are not visible to Hubble or to the 5-meter at Palomar.
So it's not just a matter of when you see it, it's that you see it at all because it can.
Correct. Correct. It's not a when, it's that you can see it at all because it's so far away, it's so dim, and it's so red. You need a special telescope that can see the red and that has enough sensitivity to see the dim. So this telescope is big. And you'll notice, by the way, if you've seen the picture, the mirrors are gold. They're not aluminum or silver. They're gold because gold is really good in the infrared and aluminum is really good in what we can see visible. So it was set up specifically to look at that color of light beyond what we can see. And that's why it works. That's why we can see farther back with it.
Usually when scientists do experiments, they're looking for something. They're not just a blank slate. Usually they're looking to verify some stuff.
Right.
What are some things that you would like to see verified or might expect to see verified?
We would like to see that we will learn and therefore be able to verify the theories of how the first stars and first galaxies formed. Because we look out now and we see spaces full of galaxies. Galaxies are made of zillions of stars. At the very beginning, did individual stars form and then coalesce to become galaxies? Or did we have big disks of gas form into what became galaxies that condensed to become stars? Did black holes form and then galaxies form around them? Or did galaxies form and black holes condense at their centers? And so these are some of the very big questions. And again, you have to look very far back in time, right? We're trying to find out what happened as these things first formed. And this telescope will let us do that. So I think those are probably the biggest, deepest things that we don't have an answer to yet.
Okay. And I suppose once you start learning those things, you might learn finally the Big Bang. The Big Bang is false. That's my theory, because it just seems too strange to me that there would be nothing, 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 nothing for an eternity. And for no apparent reason, pow, everything happens. To me, it's more
That is,
likely that there is a yo-yo effect. There's a bang and an expansion and back and forth, and maybe that's gone on forever. I don't know. But one big bang out of the blue doesn't seem right to me.
I don't think any of us like that. I think
Oh,
all
God.
of us would like to know some form of, what launched this and why and how. And it's hard to, we can never directly observe it. We have to indirectly observe it to say, okay, if this happened, what do we see today that would tell us that that's where it came from? And I consider myself a reasonably intelligent, reasonably well-read person, but there are people, way beyond me who are working on that problem, because it's a very difficult problem. It's very important physics to tie gravity and particles together, and somebody's going to do it somewhere along the line, maybe in our lifetime, which would be cool, because then you and I would get to find out while we're still here how gravity and particles work together. That would be wicked cool.
Oh, God, yeah. So let's talk about you a little bit. I'm fascinated by you. You're a very achieving dude.
Thank you.
I've talked about this before, but I want to remind folks that you, at your compound in the White Mountains of New Hampshire, have built your own observatory, and you have built telescopes, and you're very much into teaching people using not only the telescopes, but now, so I suppose you would call it, well, not telemetry, but using the internet to bring people real-time vision of what's going on. Can you explain what you do and how you use it?
Sure. So the program that I run, called Mountains of Stars, is an attempt to connect people with the environment and with the universe, and to get them to have a much better understanding of where we fit in, and therefore to treat things better. And for many years, we did these programs in person with telescopes and things. But COVID made it almost impossible to do public programs. Right? We couldn't gather in large groups. We couldn't have people near each other. So in addition to the presentations and workshops, I was able to get something called a Malin cam, which is this incredibly high sensitivity of video camera system that you put on a telescope. And it puts images right onto your computer. And of course, once you're on a computer, you can do anything, right? We could be doing this. If we were on a nighttime and the sky was clear, instead of seeing my face, you could be seeing what the telescope is seeing. And that is amazing, because it means that I can be doing programs for anyone, anywhere. So as a matter of fact, one of my colleagues is a science teacher in Lynn, Massachusetts, and we now do observing programs for all the middle schools on the North Shore, because the students can be on Zoom and be watching what's happening. It's a really great way to be able to expand our reach and give people a real live experience, even though they can't touch the telescope directly. The technology is fantastic. It's really, really great.
It looks good, huh?
Yeah, it looks fantastic.
We were actually thinking about doing something live at some point, and we were waiting for the weather to get right, and we never did it. We still can do that, right? We can
Absolutely. Yeah, we got to pick a time when the
Okay.
situation is good, and we can know ahead of time, so we can, you can promote it. We can get people on, and it would be fantastic. I can show you all sorts of cool things through a telescope. It's really, the technology is fantastic.
Yeah, when I was up to your house, you showed me the sun in you had the telescope pointing at the sun. You could see the flares coming off the sun.
Yeah, yeah.
Which is, it's shocking to see. One final question, which is unrelated. Well, it's only slightly related. All these rich folks taking other rich folks up into space. Is there a larger value to that, or is that just kind of a waste of time and money? I mean, that's not. Alan Shepard did that in the 60s. Is this worthwhile scientifically? Is there any larger gain to it, or is it just a vanity ego thing, a waste of money?
I think there's a little of both. There is value to it, because what we've now done is sort of transferred space development from a government-funded, contractor-based thing to independent companies that are going and doing it on their own. And that's a tremendous thing. I mean, the only reason we can do things with the space station now is because an independent company, Elon Musk and his crew, have built launch vehicles and spacecraft, and we can send people and supplies back and forth. NASA doesn't supply the space station. NASA contracts with this company that takes care of it for them. And so these technologies have been developed because there's a commercial value to doing that, right? So these various flights are being done by these companies in part to test out their technology and to promote their capabilities, and to build a business around that to make it commercially viable, which then provides all of us the technology to do these things.
All right.
But there are some very serious trades. So there are major issues right now with, for example, the Starlink and other OneWeb, the other big internet satellites, because there are so many of them, they're actually creating problems in space for launching things, for space debris, for telescopes and astronomy, because we have these bright things flying through the sky. There's the potential to have between 40 and 50,000 satellites up constantly to provide this internet service. And you can say, look, there's a great value to everybody having internet wherever they are. And I'm not going to argue with that. But there's also a great value to having space, which is a safe place to launch and orbit other things. So it's a difficult situation, but it's tied to the ability to have independent companies develop and use technologies without it being they're supported.
They really crank out the rockets these days. I mean, it used to take them forever to build. NASA to build one. Here it is. Here's the one. It better work. Do they have a conveyor belt making rockets these days?
Essentially. Well, there are two things. There's the conveyor belt aspect of doing it. The other thing is they're building things that are reusable. Oh. So all of SpaceX's launch, the first stage, those first stages are reusable. They land them back and use them over and over again. So that's obviously more economical, right? You use your same car every day. You don't go get a new one every day.
So they have, where do they land them? In the water with parachutes?
No, actually, they have a landing platform that does sit out in the ocean. It floats. It's a little docking barge. And the thing actually, with rockets, lands right on the barge.
No way.
It's amazing. Yeah. Yeah.
Oh, that is big. That is
go to YouTube and just, search for, SpaceX first stage recovery.
All right.
And a few minutes after launch, once that thing's expended, it comes down and lands itself.
Must take a lot of fuel to do that.
It takes some fuel. Yep.
Okay. Doug, well, this has been a half an hour. It's probably a good stopping place. I look forward to speaking to you again. It's been far too long. I hope we can do this on a kind of regular basis. Maybe before you say goodbye to me, we can schedule the next one. After we're off the air.
Let's plan that. Yeah, that would be great. I love doing this. Yeah, for sure. Let's do that again.
Doug Arion, astronomer, instructor, teacher, good guy, a ski instructor. Thanks so much for being with us. Bye-bye.
Thanks. Take care.
Okay, we'll be clear in